I feel like you guys should know by now that if I'm sitting, this is probably a pretty easy lecture without a lot of math and without a lot of info in it, but still something I gotta tell you. So I'm sitting today. So we're looking at strong acids and bases. That's something we've talked about before with strong electrolytes. A strong acid or a strong base is a strong electrolyte which dissociates completely in water. Water completely breaks it apart, and if I'm not mistaken, you've gotten these lists of strong acids and strong bases before, like long time ago, like September. So here they are again. You will need to know these and you'll need to recognize these as a strong acid. Hydrochloric, hydrobromic, hydroiodic, but not hydrofluoric. Hydrofluoric's nasty either way because fluorine's so electronegative, but it is not technically a strong acid in terms of dissociation. Nitric and sulfuric are two that we learn as the acid names in chemistry. They're two I make my kids learn there. But then I think these two are weird. Chloric and perchloric are the hardest two for me to remember. So you will need to know these. I always do binary acids, but not hydrofluoric, then nitric and sulfuric, and then the two weird chlorine ones. HClO3 chloric and HClO4 perchloric. These are great because if these break down totally, you can calculate the pH right from the amount of hydrogen. It's very easy because you're just like, oh, it's 1 molar in hydrogen because it all broke down. My only warning on this is keep your eye on sulfuric. It's diprotic. It has 2 hydrogens it can give, and you would need to take that into account and multiply your concentration of hydrogen by 2. When you're calculating pH of the other 6, which are monoprotic acids, for a strong acid that's the only significant source of H+, and this is for strong acids, my concentration of hydrogen equals my concentration of the acid and also equals the concentration of the anion that broke down to make it. So if I have 0.5 molar nitric acid, I have 0.5 molar nitric acid to start, so I have 0.5 molar for H+, and 0.5 molar for NO3-. It breaks down completely, so the pH is easy to calculate. It's what we did last lesson. What is the pH of an aqueous solution of 0.063 molar? That's one of those icky chlorine ones. That's chloric. We're good. It's strong acid. It's breaking down completely, so HClO3 yields a hydrogen ion concentration of 0.063. The negative log of 0.063 is a pH of 1.20. That's acidic. That's really acidic. And that's good. It makes sense for a strong acid. 8 strong bases to learn. I have to change my numbering. I just looked and mine goes 1, 2, 3, or 1, 2, 3, 4, 5. Fantastic. So if yours is numbered that way, I'm not sure why Word does that. But there are 8 of them, whether it's 1 to 3 and 1 to 5 or 1 to 8. The important thing is where they are on the periodic table for the cations. If I find these cations on the periodic table, 1 through 5 run the entire line of alkali metals from lithium to cesium. Run all of group 1. When I get to group 2, beryllium does not, but calcium, actually magnesium does not either, calcium, barium, strontium do. This comes from my solubility rules, solubility of hydroxides. Think back, we learned that group 1, I was like, if it's got a +1, just break it down. Group 1 is soluble, 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 and so is ammonium. So Na through Cs are all +1, making soluble hydroxides and strong bases. The bottom of group 2 for your hydroxides are soluble, less so than group 1, but still considered soluble. Still strong bases breaking down completely in water. That came from our solubility rules. To calculate the pH of a strong base, we're going to do something very similar to the acid here. As long as your strong base is the only source of OH-, it's easy to solve because 14 minus the negative log of OH gives me pH, and 1 times 10 to the 14th, my Kw, equals my concentration of hydrogen ion times my concentration of hydroxide ion. I can use either to get my answer. So for my practice problem, I wanted to do this, because I wanted to compare sodium hydroxide and calcium hydroxide with one difference in the calculation. So 0.38 molar NaOH, it's a 1-to-1 ratio. That means I would have 0.38 molar sodium ion, 0.38 molar OH minus, and that's what I'm interested in. I know that that times my concentration of hydrogen is 1 times 10 to the negative 14th. Setting that up got me a concentration of hydrogen equal to 2.63 times 10 to the negative 14th. Negative log of that gives me a pH of 13.6. Awesome. Does that make sense? Yeah, that's a lot of NaOH, so that's a lot of OH, and a very basic solution. Good. With calcium hydroxide equal to 0.023 molar. That's a lower molarity, a lower concentration, less OH ions. I expect the pH to be a little less basic, even though, hold on, each molecule of calcium hydroxide supplies 2 OH ions. So I double my concentration of OH. Calcium hydroxide is 0.023, but each gives me 2 OHs for an OH concentration of 0.046. Same procedure, that times hydrogen's 1 times 10 to the negative 14th. Yup, higher concentration of H plus, lower concentration of OH minus gives me a pH that is slightly less basic, but still basic at 12.7. These are how I would calculate for OH being my only source of OH, like literally when I see OH, that's the OH, but O2 minus, H minus, N3 minus, some anions are able to take hydrogen from water and leave OH. This would complicate calculations. I don't think you have any problems like that. We don't see any in this class, but it was more of a warning that it's not always this straightforward. I think by now you know that. Our calculations will be of the H and OH variety here. Take home message, memorize your strong acids, memorize your strong bases, and be careful when you do these calculations. They aren't hard, but keep your eye out for sulfuric acid and calcium, strontium, and barium hydroxides contributing twice the ion concentration when they break down. Practice problems, more pH stuff, more OH stuff, very straightforward. See you later.